So 4.3 is all about some of the properties of definite integrals. And while some of them are pretty straightforward, other ones are a little bit trickier, especially if you kind of want to work them backwards. So here's the very first one, and they're not in any particular order. And the first thing is, if you want to find the area under the curve from A to B, if you were to reverse that and go from B to A, you will get the exact same thing, just opposite. So kind of what that looks like, let's say you've got a graph here, and you got some area under your curve from A to B. Well, if you're going from left to right, we expect it to be a positive area. But the truth is, if you go from right to left, you're going to end up doing your dx at the end of these things. And dx is really your change in x. And if your change in x is from right to left, think of it like if, and here a is less than b, which is less than c, so we can just go like 1, 2, and 3. So from a to b, 1 to 2, if you do 1 minus 2, you get negative 1. If you get 2 minus 1, you get a positive 1. So the order matters. And if you were to just flip the integral around, so a to b, b to a, you would get the same thing, just opposite. I use this a lot when they want you to give me things like the integral from, let's say, like 3 to negative 5. That would equal the opposite of the integral from negative 5 to 3. Most everyone wants to work left to right, so usually we would flip those around. Another good useful thing is, let's say you wanted to figure out what a to c was, but you know a to b is like 3 and b to c is 5, so then from a to c is 8, the total area of the curve. So if you get somewhere in the middle, a to b and then b to c, you can find the whole thing a to c. Okay, a couple things that need to be true for all this to happen. You can't have really any vertical asymptotes in here. You can't have b being a vertical asymptote. These kind of have to be numbers, and they have to be kind of nice. So you have a vertical asymptote in there, then you start having infinite area under the curve and all that fun stuff. But talking about just normal functions. Now, things that you can do here is you can rearrange this and like subtract this over to the other side of the equation. So then you can have like a to c minus b to c, and that will equal a to b. So you can take like the whole thing minus a part to get another part. Or vice versa, you can move this over the other side. So you can rearrange this equation in different ways, and sometimes that's a little tricky, especially when you need to use one of the opposite kind of complementary rules. Alright, another one is if you've got some sort of constant in there, it could be c, d, it doesn't really matter as long as it's a constant, you can pull that out. You can pull out any number, so like the integral of 2x would be the same thing as 2 times the integral of x dx. You cannot bring any variables out front, you can only bring constants out. And the last one, a to a, well, I'm hoping everybody kind of gets that idea. What's the area of the curve from a to a? Well, it's 0. There is no area from a to a. Alright, so most of the time you want to do the antiderivative if you can, and you want to plug in your points. But if you can't, you might just be stuck with somewhere where they give you some information. So let's try to use these rules down here. Alright, so these are pretty slick here. Now we know that from 2 to 4 of this is 60. Maybe we know how to figure that out, maybe we don't. Plug in the calculator if we want to. 2 to 4 of x is just 6, and 2 to 4 of dx is 2. Okay, so we want to apply our rules. Well, 2 to 2, that's just 0 because it's the same endpoints. Okay, well, how do we use this one? Well, this is a constant, right? So this is the same thing as 15 integral from 2 to 4 of dx. And we know that this is 2. So the whole thing is 2 times 15, or 30. You notice we're not putting plus c at the end of this. That when you're doing an antiderivative, you can have that. But these, we're looking at getting an area under the curve. We expect just a number. So no bounds on there, no numbers, you put a plus c. When you get numbers, you kind of expect a numerical answer. Now, this next one looks a little tricky. But we really want to treat this as x cubed. from 2 to 4 plus 4 integral of dx. Okay, this first part is 60 plus 4 times, well, the integral of dx is 2. 8, so 68. And this is still 2 to 4. Alright, so that's the main thing. I'll show you a couple more examples, but that's really it for this section. So, yeah, let's try some of these out. Okay, now from this one, from 0 to 3 is 4, and 3 to 6 is negative 1. So if we want to go all the way from 0 to 6, all we're going to do is we're going to take the integral from 0 to 3 plus the integral from 3 to 6. And you notice how this all connects together all the way from 0 to 6. And that equals 4 plus a negative 1, or 3. Fun stuff. Now, if I want to go from 6 to 3, I know 3 to 6. 6 to 3 would be just the opposite of that, so a positive one. Alright, 3 to 3, I'm hoping everyone's got this. It's 0. And then the last one here, take out your negative 5, 3 to 6, f of x dx. Okay, well this integral is negative 1 times negative 5, or 5. So those are our main rules for using definite integrals. Again, the difference between a definite integral and an indefinite integral: a definite integral has bounds.